Okay, so what we're covering today are kind of two lab techniques. We talked a little bit about the last one, and then that's what the virtual lab is about, so if you haven't done that yet, do it. It doesn't, how long did it take? 20 minutes. I was like, I don't think it should take very long. You know, so if you haven't done it yet, do it, because it will give you a good visual, especially because we're not doing an actual lab on spectrophotometers right now. I hope to do one later. Just right now with hybrid, I just don't know how to make labs work. And I feel bad, like, because half don't get to do it, but then some do it. I don't know. But we do need to understand how they work. So today we're going to look at some of the graphs that we would get from doing these and interpreting them. And then we're going to talk about a second type of lab technique known as chromatography. We're going to do a mini chromatography on your desk right now. So let me bring beakers to those that don't have one. So people at home, sorry, you'll just have to watch. But we'll show you what happens here. This way you can see what it does. And then once again, I have faith in science. We'll one day be back to normal and we'll do a chromatography lab. How many more do I need? 2 more? Okay, let me grab those real quick. Somebody tell the people at home a joke.
I have one, but start here.
Does anyone know any jokes?
Okay, does anyone, can you think back to like beginning of the year, unit 1, we did an activity in class where I had a bunch of different mixtures of things. Like there was like gravel and water, there was like oil and water, salt water, and you had to come up with ways or ideas of how to separate them.
Yeah.
Everyone kind of remember back to that? Feels like a long time ago, wasn't that long ago though? One of the mixtures was blue and red food coloring. Remember that one? Because it kind of tripped most people up on how to separate it. This technique that we're going to learn does that. It just takes a little while to get going, so that's why we're going to set it up now, so we can kind of watch it as we talk. And then we'll go from there. Okay, so the second thing I'm going to give you is a piece of what's known as chromatography paper. Now you've got to be careful with chromatography paper because the oils from your finger can mess with the experiment. Okay, so I'm going to set it on your desk and just be careful when you pick it up. You want to kind of pick it up from like the edges like this, not like that. Okay, and then what I'm going to give you is a marker, and this is our sample we're going to separate today. Let it get to work while we talk, and then come back to it. I really like nowadays. I like want to get rid of half my tables, just so there's like more space. Okay, so there's a starting line already on your paper in purple or brown ink. Okay, I think of chromatography, and maybe just because I think of most things this way, but I think of it like a little race, a race of the colors. Okay, so what you need to do is you need to draw a dot on your starting line with that black marker I gave you. Okay, so like here's your strip. There's your starting line. Draw a very concentrated dot. So not big, but like go a few times around to make it lots of ink. Okay? Now we're going to put it in to start the race. Now, when you put it in, the biggest thing you have have to be cautious with is you can't let the paper slip and go under the water. What we want to do, I gave all my beakers away, is you just want it so that the bottom of the paper is touching, but then you kind of want to lean it against the side, and you can fold it at the top to keep it from falling in. You don't want your paper to drown. You just want it to be tilted in with the water touching at the bottom so the water can start climbing up the paper. Does everyone understand that? Okay, do that now. So take your paper, starting line side down. If I put too much water in yours that it looks like it's going to submerge the line, let me know. And then you can kind of bend the top to keep it from falling. Oh, perfect, Bryce. Everyone look at that. I don't want to move it because I'll mess it up. Okay, so this is their little paper, friends at home. They're sticking it in a beaker. It's quite boring right now, but it will get exciting. The race just started. Okay, everyone got theirs going? Okay, now that's kind of like watching paint dry. It's going to take a little while, so we'll just leave it there. Pull out your note packet for me, everybody. I'll kind of talk about things, but we'll come back to this in a second. So we're going to talk about Beer's Law first and spectrophotometers, and then we'll come back and talk more about chromatography as this runs its course. Okay, so spectrophotometers, once again, this is one of them. There's lots of different types. Old school ones, we have one like in the other lab and it's like this big. But nowadays they're getting much more concise and much cooler because that's how technology works, right? The basis of this, and once again, hopefully the virtual lab will help you kind of understanding how these work. But the simple idea is this, is there's a flashlight, so to speak, inside. The flashlight shines a light through the cuvette. That's what this little thing is called, is a cuvette. Okay, and then there's a detector screen on the other side. The detector can measure how much light is absorbed in the sample by how much comes through. Okay, now someone who did our activity, did anyone find the relationship between the color of light to use versus the color of the sample? So like the first one that pops up is like the sample's red. And how do I know what's the best kind of light to shine through it? Does everyone remember the connection? Yeah, Max.
What I saw was that the more opposite the color, like on the color wheel, the more the light goes through.
Perfect. Have a smiley face for that. That's the exact connection. Is complementary colors work best in this process. So a lot of times when you do a lab, that's kind of the first part is you have to figure out, okay, what wavelength do I want to use? Because you can shine any sort of wavelength, but one will give you the best results, and that's known as the max wavelength for the max absorption. From this data, we can use the Beer Law equation, which is on your formula sheet, so you don't have to memorize this equation, just need to know how to use it, is A, which big A is for absorbance, equals A, B, C. It's actually a pretty easy one to memorize, but. Now sometimes little a in other textbooks and things is actually shown by an E, but for AP they use the little a one, so that's what we'll use. Okay, that tells us the molar absorptivity, which describes how intense the sample of molecules absorbs light of whatever wavelength you've chosen. The path length B is the size of your cuvette, right? So path length meaning how long of a path is the light traveling through. The wider this is, the wider the path length. Normally A and B, normally you keep these constant for an experiment. Once again, because normally you don't have a different device to use, you don't change your cuvette size. And that is little a is based on the specific molecule you're testing, and so that doesn't change. C is the concentration, which is kind of the whole point of doing these tests, is it's a way to help us determine the concentration of an unknown sample. Once again, let's say I have some Kool-Aid, And I wanna know how concentrated my Kool-Aid is, because who doesn't wanna know that, right? But this lab technique could tell you that. First though, you have to build what's known as a calibration curve to find your unknown. So let's talk about that, and we'll look at a curve here. Okay, so first off, for most experiments, the path length and wavelength are held constant, and so it's really just about that concentration change. This is the basic procedure if you were to do it yourself. If the sample is placed in the cuvette, you do have to be extremely careful with fingerprints for this type of experiment, because if you have fingerprints on your cuvette, that's going to affect the light shining through, right? If your window's dirty, light doesn't come through as well. Okay, you select which light you want based on maximum absorption. Now, the cool thing about this is these devices, as they've gotten more high-tech, can find that max absorption for you. You just push a button, creates a graph, and you find what is the highest point. So the graphs normally look, the first graph looks something kind of like this, where this is absorption, and this is wavelength. And so then we would pick, that would be our max wavelength. So that would be the wavelength I would use to then test all my samples. Okay, once I know what wavelength I want to use, then you pretty much just do this and you say, okay, you take your sample, put it in, test it, measure the absorbance. Take the sample out, you always do a blank in between, so then you would put just a blank cuvette with distilled water, and then you test the next sample. You just keep testing, and then we'll get a graph, something like that, where this was the concentration, and that was the absorbance. Concentration, absorbance, and it should be a linear relationship, because that's what the equation ABC tells me, okay? Now, let's look at how we can use this to interpret some data. Okay, so that right there is known as a calibration curve. We figure it out by using known samples. Our question here says, okay, the student dissolves the entire impure sample of copper sulfate in enough distilled water to make 100 milliliters of solution. The student measures the absorbance of the solution and observes that it is at 0.3. So our absorption for our unknown is at 0.3. Determine the concentration of copper sulfate in the solution. So to use our calibration curve, it's just an XY matchup. So we take what we know, so I draw this with your pencil, so go to 0.3 absorption on your graph. Okay. Draw a line to your calibration curve. Draw a line down, and our concentration of our unknown would be about, yep, about 0.15. How does my face grow? It's not that evident. Questions on that? It's kind of how you read a calibration curve, is you just match it up. Now the second side is maybe doing some math or some conversions with that data. So the second part of the question says, calculate the number of moles of copper sulfate that were in the impure sample of it. So we have our molarity, but we just want moles. Isaac?
So wouldn't it be, so isn't it moles over liters, right?
Perfect. So molarity is, capital M is moles over liters. That's on your formula sheet. Side note, if you forget, continue.
Never mind, I don't know how to do it.
Oh, you're off to a great start though.
How do you divide liters to moles if it's already in the bottom? Just don't you want it equal moles?
So we want to, so this is what M equals.
Yeah.
We want to isolate just the M.
Yeah.
So in a sense, think of this as a variable like our X, we need to move liters.
Wait, Oh, it's ml equals moles, so then you just do 0.15 m times 0.1 equals the moles.
There you go, you gotta have something that is that. So what he's saying here is we're in a sense, we're gonna times both sides by liters. Right? Cancel it away. So moles is gonna be equal to liters times molarity. Okay, where liters is he took our molarity, our volume here, sorry. So our volume in milliliters. I changed that to a liter, it's 0.1. So we get 0.1 of a liter times by our molarity we just found, which just moves the decimal over 1. 0.015 moles of copper sulfate. Questions on that? Okay, so that's one type of problem you can see with this type of data is given a graph, what can we pull from it? The other type of question they love to ask about this is error analysis. They love to do that with lab questions. Is they say, okay, this happened, explain or come up with a reason of what went wrong. So let's take a look at one of those problems next. Okay, so let me get rid of this. Okay, so this one says, I'm going to read it from my paper so I don't have to look awkwardly right there. It tells us, a student uses a visible spectrophotometer to determine the concentration of copper chloride in a sample solution. First, the student prepares a set of copper chloride solutions of known concentrations. Then the student uses a spectrophotometer to determine the absorbance of each of the standard solutions at a wavelength of 510 nanometers and constructs a standard curve. So that's just describing how they created this graph. Finally, the student determines the absorbance of the sample of an unknown concentration. The student made the standard curve above. Which of the following most likely caused the error in the point the student plotted at 0.05 molarity? So first off, come up to your graph here, and what we need to do is we need to match the error, or match the flaw with the error. So on our case, that dot right there is not where it should be, based on the calibration curve. Make a little note to this that this is too low. So our problem is we got too low of an absorption for that concentration. So what we need to find here can you see my hand on the screen if I write right here?
Yes.
Yeah? Okay. So what we're looking for is of these errors, which one would show which mistake would give too low an absorption. So this is how I problem solve error analysis questions. Is I find, okay, well, what was the error? Is the error too high or too low? That's always going to be the case. Now we need to match which mistake would make it too low. Okay, question on what the question is asking first off. Sometimes that's the biggest struggle with AP questions. Yeah, Ed.
How does absorption get measured? Is it like through the path length of the that thing?
Part of it, yes. So on the other side of this is the detector, right? And so they shine the light, and the detector measures how much light gets through. And by knowing how much got through, you can then figure out how much got absorbed. But it is based on the path length, right? Because obviously something with a bigger path length is going to absorb more, because it's more to pass through. So
if it's like a shorter path length, it'll have less.
yes,
Okay.
yes, good. So that could be a problem if that was an option. Yeah, good connection. Okay, let's go through our options here. Number A says there is distilled water cuvette when the student put the standard solution in it. Okay, don't say anything out loud so everyone can think for a second. So what this is saying is there's water in here, and then I poured in my sample. The question is, does it make a change, yes or no? And then if it does make a change, does it match that it would be too low? So first off, thumbs up, thumbs down. Would having water in here already affect the absorption when I measure it? Thumbs up, yes. Thumbs down, no. Hypothesis, yes. You're giving me a thumbs up. You can have a smiley face. You're correct. Okay, so we know it's going to cause problems. Because some errors may not cause problems. Like it might not change the data. But it is going to cause a problem. Now the question is it going to make my absorption? If I have water in there already and then I pour in my 0.05, give me another thumb. Do you think is that going to make the absorption too high or too low? So it's going to make it too low. Why? Yeah, Bryce.
Because the solution will be diluted, it won't be able to absorb as much.
Is it actually going to be 0.05 anymore? No, and it's with how small this is, even a few drops are going to make a difference, right? And so if the concentration goes down, the absorption will go down as well. So that actually ends up being our answer. We'll go through the other ones just to problem solve, but A is the reason why. Okay, so the reasoning here is, once again, this is what my brain does, it says, okay, distilled water is going to lower the concentration. If concentration lowers, so does absorption. Okay, let's go through the others just so we can understand the effect it's having, even though A is the right answer. Okay, B says there were a few drops of a 0.1 molar cobalt standard solution in the cuvette when the student put in the standard solution. So now instead of water, I now actually have some excess cobalt in here. What would that do to my absorption? Yeah, it's going to make it go up, right? Because in a sense, this is going to mean an increase in concentration, right? Increase in concentration means increased absorption. So still a problem, but this problem doesn't match what happened. Now, as we're thinking through this, just to recognize that this was, they also love to do error analysis questions as a free response type problem, which means you have a variety of errors you can pick from. But the biggest thing is you've got to make sure the error you pick matches the direction of the error. And you can't just be broad. I've seen some students who just say like, oh, well, they probably spilled some. In this type of experiment, would spilling any liquid mess it up? No, because the concentration doesn't change if you spill a few drops on the counter, right? So you've got to get specific with what's going on. Okay, carrying on, it says the student uses a cuvette with a longer path length than the cuvette that was used for the standard. This kind of goes along with what Evan brought up. So if B increases in my equation, what's going to happen to absorption? It's going to also go up, right? So that doesn't match. And then the last one says the student did not run a blank between the 0.05 solution and the one before it. This one would also cause too high of an absorption because if you don't run the blank, then it just messes with how effectively, I guess you could say, the light passes through it. So, any general questions? I know that's not a lot, and it's not what I wanted to be because I wanted you to do a lab on this, but any general questions with understanding these graphs and kind of how this device works? For now. Okay, let's take a look at our races, everybody. Take a look at your paper. What are we seeing happening here? So we started out with a black dot. Now what are we seeing? And if you're colorblind, you might need someone to help
Lots
you.
of colors.
Colors are moving up.
Yeah.
Okay, the colors are moving up. Okay, let me draw a picture up here. If you want to turn, there's some notes about chromatography on page 13 in your packet. If you want to flip to that page. Okay, let me draw pictures so those at home can see what we're looking at here. Okay, so here's our paper. This is how it started. Now, it's starting to look kind of something like, okay, I know you have like, what colors do you see?
Green,
Blue,
reddish,
purple.
orange, blue.
Okay, so there's some like
Blue,
blue at the
purple.
top,
Brownish red,
brown at the
burgundy.
brown at the bottom. Anything else?
There's some red.
Some red in there?
Black.
Where's the red at, Harley? In the middle?
Mine is like
I
actual
don't have a red
red.
marker.
Blue, purple, light blue.
I'm out of markers, that's dumb. Okay, pretend that pretend green is pink. Pink, fuchsia, red, something going on in the middle there, okay? We'll keep letting it sit, but I'm gonna show you when I started last period. As we continue to let it climb and race, we'll get even more separation. Okay, is that on the screen? Can I see that? Oh, very good. Okay, and we'll let you guys go so you can keep watching it happen. So, let's try to figure out how this works. I'm gonna tell you two things about it, and then you're gonna try to tell me something about the colors. Okay, now chromatography, this is chromatography paper, there's lots of different types. You just buy the type depending upon what experiment you're doing. Okay, this particular paper is less polar than the solvent, which is the liquid. Okay? So this paper in particular, now this isn't like a true statement always, it could be the other way around depending on what you choose to use. So think for a second, what does that tell me about the different colors then? If I know that the paper is less polar than the solvent, what conclusions can I draw about these different colors? And give everyone 1 second, I think, and then you can share with us. Okay, let's do this first. Turn to your distant table buddy. Find one. You guys can do like a threesome with Evan, and you guys can do threesome with Carly. And share with them conclusions we can draw. Ready, go.
Maybe like colors of the top are
Yeah, the red one. Or I was kind of but I don't know.
Yeah. Yeah, probably. So where it's like, it's like, the
Yeah.
colors stay with the water, so they climb higher.
So we know that a black Sharpie has lots of colors in it.
Yeah.
I don't know.
Yeah, because the water is
How hot is like what color?
Yes.
Just made of
water is more.
Yeah, would you say that the one on the top?
Okay,
The water has
first off, I need to fix something. I made a mistake. Well, when I had my TAs make these strips, they used the wrong marker. The starting line is not supposed to move,
Oh.
and yours is gone. Yours is moving. So that's one problem where yours looks a little bit different because you have some brown. Like, why do theirs look so weird? Or more weird? Is your brown is traveling in the race as well, when technically, if you see on mine, I did it with a pencil, it doesn't move. So just side note, generally with chromatography, the starting line shouldn't travel with everything else because that messes up the race. Okay, second thing, someone might raise a hand, what conclusions can we draw? Yeah.
That the color that's more to the bottom is less polar than the color that's at the top.
Okay, first conclusion Isaac is stating is he's saying the lower the color is what?
Less polar.
Why?
Because you know the paper is less polar than the solvent, so on the one that the solvent that's not polar sticks to the paper more than the polar one, so then it stays more in the same place, but the polar one moves out because it doesn't stick as much to the.
Good, remember like sticks to like. And so the more polar is gonna travel with the thing that's also more polar. Good, how does my face for that? Other conclusions that we can draw. Yeah,
It kind of said like we can see like the concentrations of like what colors make up the marker.
Ooh, good, so we can see the difference in concentrations a little bit.
Yeah.
Now, obviously, this is not a quantitative type technique, meaning that way we can't measure them, but we then could then take our sample and put it in like one of these to then help us determine what they are, right? Yeah, good. I'm gonna add, I think, Aaron, you said it, it's simple conclusion, but I think it's important to recognize. Do you remember what you said?
The one at the top has less concentration.
Oh, there's something else. I thought I heard you say. It's hard to identify just saying things with masks on. I thought you said that is true, but I think you said something along the lines of that it's a mixture. Like black ink isn't just one thing, right? But it's made up of these different components. Now, the big takeaway is chromatography works through this process of intermolecular forces. Is that the intermolecular forces are different enough you can pull them apart from each other based on those forces. Okay? Any general questions before we try another problem? Okay, you can write your answer down to this just somewhere in that blank space. With some smiley faces here. Make that a little bigger. Okay. Given this chromograph here, come up with 3 conclusions about our sample. Conclusions are just something you can tell me about. Okay? It says that in a paper chromatography experiment, a sample of pigment is separated into 2 components, which we're calling X and Y. The surface of the paper is moderately polar. What can be concluded about X and Y based on the experimental results? Okay, so take a moment and write down 3 conclusions that you can come up with. Yours isn't looking as pretty because that brown is messing it up. Let's get in there. Might separate out some more. Let's get 3 conclusions. They can be simple as long as it's a true statement, it's a conclusion. And it's not something that's just told you, right? It's something you come up with. Set your pencil down when you're done with your conclusions. Okay, raise a hand. Someone share with us one conclusion that can be drawn from this data. Something I can say. Yeah, Isaac.
Is Y more polar than X?
Is water more polar than hexane? Is that what you asked?
Is Y is
Oh.
more polar than X?
Oh, you said Y. Okay, so he claimed Y is more polar than X. That is a good conclusion. Have a smiley face if you found that one as well. Why, Isaac? Why is Y more polar than X?
Because you know the paper is moderately polar, so then the one that sticks more to the paper has to be more polar.
Good, good. Another big thing that you should always, so the first thing whenever you're doing a chromatography problem is figure out, okay, what is the paper? Right, is the paper polar or non-polar? And then what is the solvent? Because it's really a comparison between the two. So what a lot of people last period missed, or maybe you did too, is that the solvent we're using is hexane, C6H14, which is non-polar. So the liquid that's traveling up the paper is a non-polar liquid. And so things that are polar are not going to get pulled very far with it. Okay? So you can also have a smiley face, technically if you wrote it the other way around. Maybe so that X is less polar than Y.
Would that work for two different statements, or would you just that count as one?
I count it as two. Two different sentences. Kind of the same conclusion-ish, but if you wrote both, you know, it's next to smiley face. Other conclusions we can draw? Anyone else write something different? Landon?
Both components came from the same sample.
Good, right? That they came, like, this sample is a mixture of X and Y. Good. Any other conclusions people came up with? Yeah, great.
I said the forces between X and Y are weak, like moderately weak, because they can be separated just by
Good, so the forces between X and Y must be at least different enough from each other that they can be separated. Good, yeah, great conclusion. Because that's one of the things is chromatography won't work if X and Y have very similar forces, right? Because then they'll just travel together and you'll never see them separate. So, yeah, good. So X and Y have different forces. Now that doesn't mean that technically X could be polar and Y could be polar, but there's a big enough difference between their polarities that we can see that separation out. So, any other conclusions or any other questions about chromatography? See a question like this on your test, can you answer it? Any other questions? Once again, we'll do the actual lab to this because it's actually one of my favorite like non-explosive lab type things. Because what we're doing is we actually separate the colors out of like candy. So we pull the colors off of M&Ms and Skittles and Sprees, and then we separate out like in a blue M&M, is it just blue or is there actually like other things in there? And then you can match it to the ingredients list to see does it match? Because there's 7 common food dyes or 7 FDA approved food colors that are used. So when you look at food color, when you look at ingredient lists, you'll see like yellow number 40, red number 3. Once upon a time, actually before scientists realized to be careful with it, there was like hundreds of different food colors. And then they realized, oh wait, most of these aren't good for us to ingest. So that's why there's only 7 now. But that's why they have like weird numbers, because like red 40, there used to be like red 1, 2, 3, 4, 5, like all these different types of red. But that means every color of any artificial thing is made up of a combination of those 7. Or comes from something natural too. So Good for now? Okay, that is it for Unit 3. Your main assignment for the weekend is to take the Unit 3 test. So, with that being said, I'll just go over this really quick right now. That means all your Unit 3 homework needs to be uploaded. I'll open any assignments that accidentally closed too early. Okay? You need to finish all AP classroom quizzes, so once again, I'll open any that are missed, and you can still take them for full points. And then upload your book notes as well. Okay? What we're gonna do now is whatever you guys want to review for the test. So some options is there's a review PowerPoint on Canvas that we could go through now together, or you can do that on your own later. B6 chose, we went through some AP classroom quizzes, that's what they wanted to do, so we can do that. We can just go through the topics of the unit and just kind of do an overview of everything. Anyone have a preference of what you want to do for your review? We got 26 minutes. Landon.
Do AP classroom.
Okay, Landon pick AP classroom quizzes. Speak now or forever. Everyone okay with that? Okay, let me pull up some. Do you have a preference of which one, Landon? Any of them?
Maybe 3.2, I think.
That one?
I don't remember my scores.
Anyone else have a preference of a specific one? Yeah.
Could we also go over 3.1 too, like one of the ones we did online?
Like the quiz for it?
Yeah.
So yeah, for the there is a review on, like a review PowerPoint on Canvas that's optional if you want to do it before you take the test. That just has some like multiple choice questions to kind of help you practice if you want to do that as well. Okay, let's try this again. Should I keep filming? If you were at home, would you want to keep watching?
Yes.
Yes? Okay, thank you. I would like you all to have taken the test by Monday at 10 p.m. That way, there'll be a new lesson on Tuesday for the next unit, but I'm going to try to make it that you don't really have much homework over the break. So you can take a breather for a moment, because I know you all need it. And we'll jump back into it for 3 weeks before Christmas. And then we take our Unit 4 test right before Christmas break, so you can go on break and not think about chemistry. Just so you know, grade-wise, this will be the last test on term 2. Because since we take the Unit 4 test on at the end of the term, we'll wait till we do corrections when we come back, so. Okay, should we start with 3.1? We'll, kind of as I go through the quizzes too, we can kind of do an overview of like what the topics are about. And then if anyone else has certain things you want me to discuss more as we go, let me know. Okay, 3.1. Okay, now something that you need to learn and accept about these AP classroom quizzes is the way AP questions are written, and majority of these are like from actual AP tests, okay, is AP questions are not a thing where you'll just know the answer, okay, that's like what general chemistry is. General chemistry has tests where it's like, how many valence electrons does calcium have? 2, you know the answer. AP questions are not like that. AP questions are really a matter of problem solving. I'll be honest, because there's a whole bank of a ton of these. Most of these, I don't know the answer to by looking at them. I have to solve them myself. Okay, so that's what you've got to learn, is you've just got to learn how to take the topics we've learned and problem solve your way through to the answer. The thing with problem solving that I want to encourage you to not be afraid of is don't be afraid, and this sounds maybe bad, but don't be afraid to step into the dark. Okay? Because that's often the only way you're going to see where to go next. Is you just got to try something, and then maybe try something else. Maybe it didn't work, so you have to backtrack. But that's typically the biggest holdup is students will look at a problem and be like, I don't know what to do. So they don't do anything. Okay, take what you know and just start figuring it out. Okay, let's go through, how long is this quiz? We'll go through a few, maybe not all of them, just so we can get an overview of different topics. If you want to pull up your actual quizzes on your phone, you're welcome to right now if you want to see which problems you missed. If you can get service in here, a little spotty, but let's start with this is a good one, and then we'll go from there. Okay, so this problem has, first off, test taking side note skill. Anytime they give you information up above, make sure you read it. Because often it, not always, but often it actually will come into play at some point in the question. So make sure you pay attention to it. So it tells us that the gas, this question refers to 3 gases in identical rigid containers under these conditions. It tells us if the pressure of each gas is increased at constant temperature until condensation occurs, which gas will condense at the lowest pressure? Okay, so the way I problem solve is I start asking questions about the question. And I say, okay, well, what does it mean to condense? What does that mean? What does it mean if a gas is condensing? Nina's going like this and green, and maybe she didn't mean to, but she's like making this motion like coming together, right? So condensation means it's not going to be a gas anymore, it's actually going to be a liquid. Okay, so what we're doing here, and the next thing I do is I create pictures. Okay, so I imagine my container, and I'm going to push it because it can move. Okay, until I turn the gas inside into a liquid. The question wants to know which gas will turn to a liquid first. Okay, everyone understand what the question is asking? Now, what's going to make something condense faster than something else?
If they have stronger bonds.
Ooh, close, not bonds. Change your word there.
Intermolecular forces.
There you go, intermolecular forces. Okay, create a little switch in your brain, everybody, okay? You're gonna program it right now. Anytime you read a question that deals with a phase change, meaning gas to liquid, liquid to gas, any sort of phase change like that, your brain should say IMFs, because that's what it's all about. But the problems never are going to say, hey, think about IMFs here, right? You've gotta turn that switch yourself, okay? So then, what I say is, well, if it's about IMFs, something that, are we looking fastest or slowest? Condense at the lowest pressure. So that means it's going to condense the easiest. So is something with high intermolecular forces or low intermolecular forces going to condense quicker? Point the finger, high or low? High. Because if they have high forces, think of them like magnets. The stronger the magnets, they're just going to start coming together on their own. They don't need me to push them together. If they're not strong magnets, then I got to keep pushing to force them together. So in a really weird way, what this question is asking is which substance has the highest intermolecular force? Now if I look at them, CH4, C2H6, C4H10, they only have dispersion forces. Anytime, side note if you didn't catch this before, anytime something is just a hydrocarbon, a carbon and a hydrogen in any ratio, it's never polar, ever. So, the heavier something is, the stronger the dispersion force. So that's why the answer is butane. Questions on that question? Okay, we'll look at a few more, because this one I think is all about IMS. And then we'll go to another topic unless people want to continue. Okay, this one says that London dispersion forces are weakest for which of the following gases under the same condition of temperature and pressure? So this is kind of the connection we just made, that the smaller something is, the weaker its dispersion force. So that's why it's hydrogen, is because of the list, it's the smallest. This one, which some people picked, is the reverse, right? The heavier one got the highest dispersion force. Why is that again? Like, what's happening at the molecular level that would make something bigger have stronger forces? Yeah, Max.
It has more electrons.
Yeah, it's all about those moving electrons, right? And the more electrons something has, the stronger its forces will be. So, good, have a smiley face for that. Oh, side note, in case, did everyone see the Smiley Face November Challenge? Okay, you can earn 20 smiley faces if you do this challenge. If you didn't catch it, it's linked to last time's What's Happening Today page. But it's due on November 30th, so don't forget about that.
Can we start it late? Is that like a possibility?
Yeah, you just gotta go back and do the other ones. So start it today if you haven't yet. It would be best, because the best way to do gratitude is to do it all for the day, right? Kind of like brushing your teeth. And just like brush your teeth for an hour before you go to the dentist, not quite the same effect. Okay, but yes, you can start today, Carter, if you haven't. Okay. Let's do, this one looked like it had some pretty good distribution of answers. Okay, so this one says the diagram above is a molecular model for a gaseous diatomic element that is just above its boiling point. Intermolecular forces between the gas molecules will cause them to condense into the liquid phase if the temperature is lowered. Which of the following best describes how the model is limited in its depiction of this phenomenon? Why would A be wrong?
You don't know if bond or making?
Kinda. We do in a sense because it tells us it's a diatonic element. What does that tell me? It's just two things and it's the same thing, right? So it's like O2, N2, F2, Br2, which means, does it have hydrogen bonding? No. So that's why that doesn't work, because it doesn't exist in this type of substance. B says it does not show how the interactions between ions and the induced molecular dipoles results in a net force of attraction between the molecules. Kind of the same thing, that force isn't even present. C is also wrong for the same reason, because it talks about permanent dipoles, but N to N doesn't have a permanent dipole, it's not a polar molecule. But it does have temporary dipoles as the electrons move, and so that's what we're looking on there. So, okay, it's hard to read how we're feeling. Do you want to keep going with 3.1? You want to look at a different quiz? Give me a thumbs up if you want to keep going with this quiz, thumbs down if you want me to pick a new topic. If you're not voting, then I'll just go off everybody else. Okay, new topic. Anyone have a choice? So kind of the main themes that this unit are, so there's IMFs, understanding those, gas laws, solutions, and then linked to solutions is like chromatography and spectrophotometers. But
Can we talk about gas laws?
yeah, do you want to like look at some problems, just talk about in general? Do you have a preference?
Anything, just a refresher. I feel
Just a
like.
refresher, yeah. So main gas law is our ideal one, right? PV equals nRT. Once again, make sure, does everyone have a formula sheet to use when you take the test at home? If you need one, let me know, I'll get you one, because this is the first test where you'll want to have that with you. Because this is on there, right? So with the ideal gas law, this equation helps us determine one variable if we know the rest. We can also use this equation to figure out changes in a system. So like if pressure and temperature are changing, we can set up the comparison equation. Do you guys remember how to do that? Evan?
The PB or P1, D1, P1.
There you go, right? So we take out what's not changing. So let's say hypothetically, like if moles weren't going to change and R never changes, we then put everything on the same side, and then you have your before and after equations. You have P1, V1, T1 equals P2, V2, whoops, T2. Once again, but if temperature wasn't changing, then you could just have P1 equals P2, V2, or or volume, like you have lots of different options for equations just depending on what the problem says. This is only used under a changing condition. So it says, hey, I was at this temperature and now I'm going to this temperature. How's the pressure affected? That's when you'd want to set this up. If the question just says, what is the pressure of the system? Then you would use this. Biggest thing to remember with Perkner is making sure the units match the R. Don't forget that you have to convert to Kelvin most of the time, and then if anything else doesn't match, to line it up. Let's see, what else is there with gas laws, or gases in general? Yeah, Evan?
On the test, will we have to use like other, variables for the, R, like for the gas constant?
Not besides the one it gives you. Yeah, I think it gives you 2 on your paper.
Mm-hmm.
And honestly, you're only ever gonna use the ATM one right now, because the other one in joules doesn't apply to this unit, so.
Okay.
Yeah, good question though, because there are other R values, like the book gives you a whole bunch, so. Let me think, what else is there with gases? It is important to understand the visual side of what a gas is, right? That they're like the bouncy balls, constantly moving. How much space do they take up? Like the atoms themselves?
Very good.
Like none, right? Remember like the balloon in the liquid nitrogen, right? The balloon went completely flat because the atoms themselves don't take up much space. But their movement takes up whatever space they can, right? Pressure is a measure. Keep in mind, pressure measures force over area. So if you're ever trying to understand or explain pressure, pressure is all about how hard and how often things are hitting a container. The harder they hit, the more often they hit, the higher the pressure becomes. We do also have this other equation on your formula sheet of dealing with total pressure. So if you ever have a question that deals with like a mixture of gases, pressure is an additive property. So they can add together to get you the total pressure. On that same line, we can find a partial pressure of something by taking the total pressure times by the mole fraction. So moles and pressure are directly linked to each other, meaning the more moles you have, the more pressure you're going to have. Let me go to okay, so one thing to recognize here is once again with pressure, so this actually is a data table from before. These questions are typically actually linked together. But what it shows us here is that if we have 3 identically sized containers, but this container has a higher pressure within it, what is that pressure telling me about the inside of that container? How can one box have a higher pressure than the other boxes?
There's more stuff in it.
Yeah, so it's like AP's tricky way of saying, hey, there's more in this box than in the other boxes.
Isaac Jensen to the attendance office for a few minutes.
Sure.
Go.
And so just kind of something to recognize that what pressure tells you. Because often with gases, we don't measure them by mass, because like measuring a balloon, like that's hard to do. So we typically measure it through the pressure, but the pressure helps us understand what else is in there. So it's kind of mostly it for like the equations that you would see. The other thing is remembering where the ideal gas law fails you. So under 2 conditions, this won't work. So remember with pressure, what do I want my pressure to be like if I want the ideal gas law to work? High pressure or low pressure? Think of if I want it to behave like a gas, If I want my gas to be a gas, do I want high pressure or low pressure? Low pressure, right? Because if you apply pressure, it's gonna condense it. Temperature, do I want high temperature to be a gas or low temperature? High temperature, right? So if you do experiments with low temperatures or high pressure, it's going to mess up your data most likely. So, once again, that's more likely they would tell you, be like, hey, if we were to do it under these conditions, right, you're not gonna have to like know exactly where, but let me think. That's all I can think of with gas laws. Any questions that brought up? Let's take a look here. Pick up the most missed question from this quiz and talk about it. Oh, where'd it go? I want to see the data from you guys. Looks like most missed. That one or this one? Look at this one. Okay, this one says equal masses of 3 different ideal gases are mixed in a sealed container. If the temperature of the system reaches, if the temperature remains constant, which of the following statements about the partial pressures of gas is correct? Why would A be false? If you have 3 gases, why are their pressures not equal? Bryce?
Because their pressures could vary, like Y could be a super high pressure and X could be like a super low pressure, which means that it wouldn't be 1/3.
Why?
It would be,
Why could it be higher than the other? What's it
Because-
dependent upon?
What's the pressure dependent
Yeah.
on?
Yeah, if they're all the same temperature, why would one have a higher pressure than the other?
The molecular weight.
Good, like the mass of it, right? As well as how much is in there, right? So good. So this could be true, but it's not like guaranteed to be true, right? B says it depends on the intermolecular forces of attraction. Why is that false? What state are these substances in?
Yeah.
Gas. IMFs and gases are the theme. Right? Remember, the bouncy balls are moving too fast to ever link up. Okay? Obviously, C's our answer right there because it depends on the masses of them. Going to the other one that says it depends on the average distance between the molecular collisions. Not really going to affect the pressure because the pressure is just based on how often, how hard they hit, not where they hit. And then, oh, looks good. No one actually picked that one. And then the last one says it can be calculated with knowledge only of the volume of the container. But we'd also need to know, right, how heavy they are and how many you have. So, any other questions about gases? About 3 minutes. Do you want me to just pull another one from this quiz while we're looking at it? Next one, let's look at this one. Okay, this one says diagram 1 shows equal molar samples of 2 gases with a removable barrier so that each gas occupies the same volume. The barrier is carefully removed as the temperature is held constant. Diagram 2 above shows the gases soon after the barrier has removed. Which statement describes the changes to the initial pressure of each gas and the final pressure of each gas in the mixture, and also indicates the total pressure? So first off, what you have to recognize here is if volume gets bigger, what's going to happen to pressure? It's going to go down. So since the volume doubled, the individual partial pressures are going to get cut in half. But then the total pressure, once again, is just the sum of the individual ones. So kind of just recognizing, I think most people picked that, got it wrong, this one. They said the partial pressure of each gas is half, which is true, but the final total pressure is the same. What's the difference between those two questions?
The the pole
The
pressures.
Oh, just that, huh? So just neglecting to pay attention to that, the bigger volume is gonna cut the pressure in half. Because if each of the individual ones get cut in half, the total pressure, right? So, this is a great example of how AP questions, you've gotta be very careful with how you read them, right? Because it's like literally one word difference in answers there. But, any other questions? Yeah, Matt?
Wait, how come, it says, the final total pressure, in D, it says, the final total pressure is the same as the sum of the initial pressures of the two gases. So, oh wait, never mind, I see it now.
Oh.
I said it out loud.
That's sometimes all it takes, is just say it out loud. I guess that's one of the benefits of taking tests at home. Is if you want to talk to yourself while you're taking it, you could. Sometimes that can be helpful. But okay, good luck. As always, remember, just do the best you can the first time around on the test. We'll fix it later, but the best way to fix it is if we actually tried our hardest the first time. Because then we can get a true evaluation of where we're at, what we're confused with, and what we need help with. So, and then I'll see you guys someday again. Who knows when?
Like 2 months.
I know, huh? Yeah. I guess you'll see me next week on the camera. Right, so tune in for that. We'll have a lesson